Hello everyone, welcome to the initial related rates lecture. So we're in section 2.6, I'll call this 2.6a. Go ahead and open your book to page 146. And with related rates, so this is mostly word problems. We know that the derivative, so you'll need to get your pre-printed notes out, and we'll be using these same pre-printed notes for the next 3 lectures. So the derivative represents instantaneous rates of change. So for related rates, you want to think about time. Time is the independent variable. We always differentiate with respect to time. So dt will always be on the bottom. And we're going to use a little procedure here to work all these problems. We're going to determine what we want, write that down. What we know, we're going to write that down. And then relate what we want to what we know. And it's almost always some sort of geometric equation that you've learned in the past, whether it be the Pythagorean theorem or the area of a circle or the circumference of a circle or the volume of a sphere. It's always going to be something like that. Okay, so our first problem we'll call the pebble problem. So consider the waves a pebble makes when thrown into a pond. So you think about, you throw a pebble into a pond and you have these concentric circles, this wave of circles that will emanate from where the rock splashed into the pond. So how fast is the area changing 2 seconds after the stone hits the water if the radius is increasing at a rate of 6 inches per second? Okay, so we're going to follow our little 3-step procedure here. So we've got the pebble problem. Okay, what do we want? Well, we're going to want to write it down in calculus terms. And let's say we have the pebble there. It hits the pond, and you've got these waves expanding in concentric circles. Those are bad circles, but it's the best I can do. We want to know how fast is the area changing. So that would be dA dt. The way, this is just nomenclature that means change in area with respect to time. Okay, how fast? So you're going to have time involved. What do we know? All right, we know, if you'll look at the problem, that the radius is increasing at a rate of 6 inches per second. So we use A for area, we're going to use R for radius. So we know dr dt, the change in radius with respect to time, is equal to 6. So 6 inches per second. All right, if you want to put the units, we can. It's equal to 6. Now relate. Well, we want area, we know radius. We're going to use area equals pi r squared. That's the area of a circle, and these are circles, right? Okay, so what you're going to do is differentiate this equation. So we're relating what we want to what we know. What we want, area, what we know, radius. We're going to differentiate with respect to time. So instead of doing d over dx, we're doing d over dt. Well, there's no t's in this equation, so everything is going to be chain rule. So the derivative of a with respect to time is going to be dA dt. And then for pi r squared, remember pi is just a constant. Bring the 2 out front. It's going to be 2 pi r. And then the derivative of r, dr dt. You can't forget that part, but you probably won't, because you know you're going to have to plug 6 in somewhere along the line. Now, we also know another important piece of information, and that's the radius at 2 seconds. Okay? We know that the radius is increasing at a rate of 6 inches per second. So the radius is going to be 2 seconds times 6 inches per second. So what's the radius after 2 seconds? It's going to be 12 inches. Now we don't plug that in until after. Don't plug in. We don't want to put that up here. Don't plug in until after differentiating. Okay, but now we can plug in the ADT. That's what we're trying to get. The change in area at 2 seconds. So it's going to be 2 times pi. The radius right here is 12. And then dr dt we know is 6. All right, 12 times 6, 72 times 2, that'd be 144. So it's 144 pi. And area is always squared, right? So inches squared per second. If you're not sure about the units, just go ahead and plug them in. So it would be, this unit would be inches, this unit would be inches per second. So inches times inches is inches squared, and then you have per second. All right, that's the procedure we want to follow, and after we do a few of them, it'll get easier. Okay, but these are pretty interesting word problems here. All right, let's move on. Turn the page, and you're going to see on your note sheet the ladder problem. So this is a famous problem. Okay, it says consider a ladder it's 13 feet long, that's sliding away from a wall. How fast is the top of the ladder falling when the base slides at 6 feet per second when it's 12 feet from the wall? Okay, let's draw this out. A lot of times it really is helpful to draw the situation out. So we've got a ladder. Like that. We know the ladder is 13 feet long. That isn't going to change. We also know that the ladder is sliding, all right, 6 feet per second. So the ladder's sliding down. It's going 6 feet per second. The way I've drawn it, it is to the left. And we want to know how fast the top of the ladder is going. So we want to know what this down arrow represents. Let's call this length, in fact, I'm going to draw that up here, y, and this length x. Okay, so what do we want in calculus terms? How fast is the ladder falling we want dy dt because I've labeled that vertical component as y. Okay, so how fast is y changing with respect to time? What we know is that dx dt is equal to 6 feet per second. All right, relate. Well, what does this look like? What geometric shape? It's a right triangle. We're assuming that the wall and the floor is 90 degrees. It's just a right triangle. And we would have x squared plus y squared is equal to 13 squared. So that's just the Pythagorean theorem, which in my classes we just call Pythag. Now I'm going to differentiate that equation with respect to time. So that would be 2x dx dt plus 2y dy dt equals the derivative of 169 would be 0. We want dy dt, so let's solve for that. We have 2y dy dt is equal to negative 2x dx dt. Solving for dy dt, that's going to be negative 2x dx dt over 2y. And the 2's will cancel, so that's negative x dx dt over y. So you've done your calculus. Now it's a matter of plugging the numbers in. Well, we know that it's 6 feet per second when x is 12. So what does y equal? Because we're going to have to plug that in. Well, we know that this is a right triangle, so 13 squared is equal to 12 squared plus y squared. So y squared is equal to 13 squared minus 12 squared. That's 169 minus 144. So that's going to be 25. So square root of that, y is going to be 5. You might also remember that this is a famous right triangle. It's one of those integer right triangles, 5, 12, 13. Kind of like 3, 4, 5, 5, 12, 13. Okay, so now we're going to plug those numbers in. We have negative 12 for x. dx dt is 6. And then y is 5. So that is negative 72 over 5, which if you want it to be in decimal, this is completely fine. But that'd be negative 14.4 feet per second. So the unit, how fast, the question is how fast is the ladder falling down? Yeah, that's a velocity. So that would be in feet per second. It also makes sense that it's negative because it's going down. So that worked out as well. If you weren't sure about the unit, just put the units in. Feet, feet per second, feet. All right, and feet and feet will cancel, and you're left with feet per second. All right, I hope once you get used to these, I feel like these are some of the most interesting problems that we've had yet. It's pretty cool that we can figure these out. All right, I've got a couple of non-word problems from the textbook. And then we'll talk about the homework assignment. So we're going to do example 2. On page 146. And let me bring that into view because you have several of these in homework for today. So we're given this equation. We're given dy dt. are in number 2, we're trying to find dy dt when x is 3 and dx dt is 2. Okay, so what we could say is that we want dy dt, we know dx dt is 2, and we're not having to, this is not a word problem. They went ahead and gave us the equation that we're going to differentiate with respect to time. So we have y is equal to x squared minus 3x. We're going to differentiate that with respect to time. So dy dt is equal to 2x dx dt minus 3, but also there's a dx dt there. Okay, because the derivative of x is dx dt. Okay, let's factor out a dx dt. And what you have is 2x minus 3. Okay, part A, what we're given is x is 3 and dx dt is equal to 2. So dy dt, we're just going to plug in. It's going to be 2 times 2 times 3, plugging in 3 for x, minus 3. So that'd be 2 times 3, which is 6. There's no units there. All right, part B, we are given, we want to find dx dt. X is 1, and dy dt is equal to 5. All right, so plugging in here, we would have 5 is equal to dx dt, what we're solving for, times 2 times 1 minus 3. So 5 is equal to dx dt times 2 minus 3, which is negative 1. So dx dt would be 5 divided by negative 1. That is negative 5. Fantastic. Not bad at all. Okay. And the last example, so you turn your notes, one more, is number 8. So we've got one involving a little bit of trig here, so you might want the unit circle handy. For number 8, we have y is equal to sine x. I'm just going to work A and B. There's no reason to do all 4 parts in this example because it's just a matter of plugging things in. So we know we're going to have to differentiate this with respect to time. So dy dt is equal to cosine x dx dt. Okay, so let's answer part A. In part A, we're given that x, let's see, we want to know, reading the instructions, so we've got some instructions here. Dx dt is 2. We want to find dy dt. Okay, so we know dx dt is equal to 2. We want to find dy dt, and in part A, x is equal to pi over 6. So dy dt is equal to cosine pi over 6 times dx dt, which is 2. Well, the cosine of pi over 6 is the square root of 3 over 2 times 2. The 2's will cancel, and you have the square root of 3 centimeters per second. All right, part B, dx dt is still 2. And this time x is equal to pi over 4. So dy dt is equal to cosine of pi over 4. So I'm just plugging into this equation right here, times 2. That's going to be root 2 over 2 times 2. The 2's will cancel, and that's root 2. All right, and remember, just your unit circle, it's cosine, then sine, so root 3 over 2 for pi over 6, root 2 over 2. And then you can, if you're just dying to do them, you can do the other two. So let's talk about the homework. The homework is on page 146. You're going to do 1, 3, 5, and 7. Those are from these last two examples, okay? So you should be able to use those examples to try to get the answer. And then there's a couple of word problems, 13 and 17. And I do give you the hint on number 17, you need you'll be relating the volume of a sphere, and that's on your notes, but it's 4/3 pi r cubed. Okay, so you will be using this equation, and I don't expect you to remember that for the test. If I give you a formula that fancy, then you will be given that on the test. All right, good luck on these. This is your first try at these, so do your best, and then you can watch the solutions video for those that you had trouble with. Talk to you next lecture.